So good morning, everyone. This is a public key cryptanalysis session without isogeny. So we will have three talks on cryptanalysis, and the first one is on the harness of the finite field isomorphism problem by Dipayan Das and Antoine Jou, and Dipayan will give the talk.
Hello, everyone. So the title of my talk is on the hardness of the finite field isomorphism problem, and this is a joint work with Antoine Jou. So for cryptography, we rely on the assumptions of hard problems. Most problems in the literature of lattice-based cryptography are believed to be hard based on a transformation to a lattice problem. And the lattice problem is known to be hard in both classical and quantum computer. In this talk, I'll present some counter-example where this transformation doesn't work and we might run into problem. To start with, let's give some reminders from the finite field theory. For any prime number q and integer n, there is a unique finite field of order q to the power n, but we can have different representations of the finite field using some irreducible polynomial. So what you can do is you can view the finite field as polynomials over fq modulo some irreducible polynomial. So you take different irreducible polynomials and you have different representations of the finite field. To explicitly find an isomorphism between the representations, what you need to do is find the root of one irreducible polynomial in terms of the other representation of the finite field. So in our purpose, we need two representations of the finite field. One is a private representation, which is a sparse and ternary irreducible polynomial that I will refer as little f of x. And there is a public representation that is uniformly at random from the irreducible polynomials over fq that I will represent as capital F of y. So the FFI distribution is defined in the following way. We sample small linear combinations of powers of x and output its representation in the public representation. So the finite field isomorphism problem was introduced at PKC 18, and it states the following. Given arbitrary many samples, decide if they come from FFI distribution, that is if they have a good representation in some private representation of the finite field, or they are just picked at random. So this is basically the decisional FFI problem. And if I just give a toy example, even for a ternary representation in the x basis, the y basis representation looks quite pseudo-random. The authors proposed lattice reduction algorithm to solve this problem. So what you can do, you can consider a query lattice that is generated by the columns of the matrix whose ith row is given by the ith sample in the set. So for FFI samples, there are unusually short vectors inside this lattice because there is a good representation in some hidden finite field representation. But for uniform samples, it's highly unlikely to have such short vectors inside the lattice. And once your lattice reduction algorithm could able to distinguish the two cases, you can able to solve the problem. And the lattice reduction algorithms are believed to be difficult to perform in practice. The authors also propose a fully homomorphic encryptions. So the basic idea was to use many encryptions of 0 to encrypt the message. So here it works in the following way. So to encrypt a bit, you pick an FFI sample and multiply it with a small integer p, which is equals to 2 in the rest of the talk. And then you add the corresponding bits you want to encrypt. To decrypt, you use your secret isomorphism to go back to the x basis representation and just take a mod p operation. Since the x basis representation is small, once you do this mod p operation, everything cancels out and you get the message back that was encrypted. Additionally, if you add to ciphertext and then decrypt it, you get the addition of the corresponding messages. Also, you can do the product of ciphertext and decrypt it to get the corresponding product of the messages. So a small thing to note here, that after multiplication in small representation, the coefficient can grow really fast. And that is the reason the authors use this ternary and sparse constraint to bound the coefficient growth after multiplication. So for our purpose, we need the trace of a finite field, which is defined as the sum of the conjugates. This is linear, which can be computed in polynomial time, and this is invariant under any basis representation. So it doesn't matter if you are dealing with a good representation or the bad representation, the trace is going to be same. If the irreducible polynomial is sparse and ternary as used in the FFI distribution, then you can explicitly find the absolute value of the trace of the polynomial x basis, and this is basically done expressing the trace of the polynomial x basis in terms of the symmetric polynomials sigma j's. So for the interval 1 to n by 2 minus 1, all the symmetric polynomials are 0 by definition. Then there is no contribution inside the sum. All the sigma d's are 0. So the trace is not going to contribute anything. So it's going to be 0 every time. For the range n by 2 to n minus 1, since the first half of the symmetric polynomials are already 0, the only solution for Ri's that is going to contribute in the sum is for the value Rd1 and 0 elsewhere. And this gives a simple explicit formula for the trace of the polynomial x in the interval n by 2 to n minus 1. So this is basically the absolute value of the trace of powers of x is d when the corresponding symmetric polynomial sigma d is non-zero, and 0 when the symmetric polynomial is 0. So why do we care? So we care because once you know the polynomial x basis, the trace of the polynomial x basis in absolute value, we can just use linearity argument from the trace to bound any small representation in x basis. And because the trace is invariant, the trace of the FFI samples are also bounded. And the bound is like a small factor of n squared. So just with this observation, we have a very simple attack on the decisional FFI problem. So you have arbitrary many samples. You compute the trace. If they are all bounded by a factor of n squared, output FFI distribution, otherwise a uniform distribution. Because for uniform samples, the trace is going to be uniformly distributed. So we can extend this to get a semantic attack on the fully homomorphic encryption scheme. So first, let n is odd, that is p is not a divisor of n. Then the trace of the ciphertext is going to be small. And then if you take this mod p, you get 0 when the message was 0, and 1 when the message was 1, because trace of 0 is 0, and trace of 1 is n, and p is not a divisor of n. And if p is a divisor of n, that is if n is even, then trace of 0 and trace of 1, mod p both gives 0. So we need to do a small modification. So what we do is the following. We can pick any arbitrary FFI sample, that's what I call C star, such that the trace of the arbitrary FFI sample is not a multiple of p. Then the product of the ciphertext with the dummy FFI sample that you have picked, C star, is also going to be small, and this is because of the choice of the irreducible polynomial, sparse and ternary. Then if you do this trace of the product of ciphertext with the dummy FFI sample, mod p, you get 0 when the message was 1, message was 0, and 1 when the message was 1. So you have a semantic attack on the both cases of n. That's what I was going to say. Thank you, and happy to take questions.
Is there any question?
Just a quick question. You mentioned the crypto system in 2018.
Yes.
Was there any sort of anything before that, or is that the first?
So I think this is the first proposal. After that, there was another signature scheme. But the assumption behind that signature scheme was quite different. It's like using PQ and true sign using this FFI problem. But the assumption is quite different than what they have stated initially in the PKZ paper.
Thank you.
Okay.
My question is, does your attack still apply if the modulus is very small?
No, so it has to be some factor of n square at least. But for homomorphic encryptions, like what they proposed, for that you need this modulus to be sub-exponential. And for that, like our bound is quite fine.
Oh, got it, thanks.
Okay.
So I have also one question.
Okay.
Have you tried to recover the secret key, or you can prove that it's difficult?
Sorry, I couldn't hear you.
Have you tried to recover the secret key?
Secret key, like the hidden isomorphism? So yes, we tried in the paper to find this secret isomorphism, but in the original paper, the complexity was n factorial. Like you need some combinatorial argument to find the isomorphism. But in the paper, what we did that, okay, you don't really need that that factorial part. You can just avoid it and just, find some shortest vector inside a lattice to solve it. So we tried it, but it still seems to be hard. But just solving the decision problem gives you a semantic attack. So that's what we think is more interesting for this talk.
Okay, thank you very much, Dipayan. So the second talk is a new time memory trade-off for success sum, improving ISD in theory and practice by André Esser and Floyd Zedinger. And Floyd will give the talk.
Yeah, unfortunately, it's Andre giving the talk.
Sorry.
No worries. First of all, I want to give the credits for creating this presentation to Floyd, and I'm very sorry he cannot be here to give the talk himself. So yeah, let's talk about our paper. So in our paper, we give new time memory trade-offs for subset sum, and we somehow unify the quite diverse landscape of trade-offs out there by outperforming almost all of them. And those also translate to information set decoding algorithms, which are the best algorithms to attack code-based crypto. And we also implement our techniques and obtain new record computations. And from there, we obtain new bit security estimates for suggested parameters. So let us define the random subset sum problem. So for subset sum, you're given n integers mod 2 to the n, and you're asked to find a subset of them of size n over 2 that sums to some target value t. And we will represent such a subset by a binary vector e of length n that simply indicates if the elements are part of this subset or not. So this vector has Hamming weight n over 2 then. And why should we care? Well, it's a cryptographic hard problem which is post-quantum secure, but more, to be fair, it's more an algorithmic tool in cryptanalysis. So better algorithms for subset sum have implications to other hard problems, as for example, as I mentioned with the information set decoding algorithms. And information set decoding algorithms use a lot of memory in practice, so this somehow motivates studying time memory trade-offs. Before I can explain our time memory trade-offs, we need some building blocks, some puzzle pieces. So we will first discuss the basic meet-in-the-middle algorithm and see a memory saving technique introduced by Schröppel and Shamir, and then bridge our way via the representation technique from Haugraf, Graham, and Zhu to the Becker-Courant-Zhu algorithm, which is the basis for our trade-offs, and then we will see how our trade-offs work and how they fit in the picture. For the basic meet-in-the-middle algorithm, you have this sum, and you simply split it in two parts, the first n over 2 elements and the second n over 2 elements, and then you enumerate both For both halves, you enumerate the xi's and the corresponding subset sums you store in those lists here. And then you simply search for one element between those lists that sums to t. And it's not hard to see that these lists are of size 2 to the n over 2, because there are that many candidates for the xi's for each of the sums. And actually, finding this subset sum that sums to t can be done in time linear in the lists by some sorting and searching. And so we get an algorithm with time and memory complexity 2 to the n over 2. Now, Schröppel and Shamir suggested to improve the memory by splitting the initial sum not in 2, but in 4 parts of equal size, n over 4 elements. So you get 4 lists, you enumerate those candidates, and so how do we get from there to the solution then? That's again by merging 2 lists at a time, but we cannot merge to t now because these elements, all of 4 of them, sum to t. So we merge on some artificial constraint t1 mod 2 to the l, where l is smaller than n. So it's like some l bit constraint that we introduce there. And then we perform the usual matching that we did in the meet in the middle. But of course, there's only one combination in the lists that sums to the solution. So there's only one t1 for which this will work. So we don't know it, so we have to iterate over it. And since we iterate over it, you will see that if you do the math, it's an algorithm that has the same time complexity as a meet in the middle, but the space complexity is only a square root of it, because we could start with smaller lists by this initial splitting in four sums, and then we could keep the list small by introducing this artificial constraint. So how do we improve time-wise from here? That's done by the representation technique by Haugoff, Graham, and Zhu. And the idea is to first blow up the search space, which might seem like a bad idea in the first place, because if you recall, we could only improve with the Schröppel-Shamir algorithm because we started with smaller initial lists. If we now blow up the search space, then these lists will become larger. However, the idea is also to increase the amount of available solutions, of representations of the solution. So how does this look like? So for the meet in the middle, we were using this disjoint elements in the lists, so where we're enumerating them on n over 2 of the, they had support on n over 2 of the coordinates. And for the representation approach, the elements have support over the full n coordinates. And this gives multiple combinations to represent the solution as sum of from such domain. So maybe that's a bit abstract. Let's look into an example. So here, if the exemplary solution is this vector of length 8 and weight 4, then there are 6 different possibilities to split the support of this vector on 2 vectors of length 8, weight 2. And more generally, there are n over 2 choose n over 4 such possibilities. So in summary, if we use these domains instead, then we increase the domain size from 2 to the n over 2 to 2 to the 0.81n. But on the other hand, we also increase the amount of available solutions from 1 to 2 to the n over 2. And we already see the quotient is getting better. But how do we get a better algorithm from here? Because now if we simply enumerate this search space, we will simply enumerate the solution multiple times, and we will enumerate more than before, so the algorithm will be worse. So this is done by Becker, Coran, and Zhu, and therefore they try to only enumerate a respective fraction of the search space, such that we, in expectation, find one of those representations. So how do we enumerate a 2 to the minus n over 2 fraction of the search space? So here we start at the root of a tree where we will finally enumerate the solution. And we construct this solution again as a sum of 2 elements from these representation domains we've seen. And we will introduce some arbitrary constraint, mod 2 to the n over 2. So this is an n over 2 bit constraint, and we have seen, like in the Schröppel-Shamir algorithm, I think I forgot to mention it, like since we know that the subset sums to t in total, if you fix the constraint for one side, you know that you have to use t minus this constraint on the other side, otherwise they do not sum to t in total. So meaning this is really a constraint of size of n over 2 bits, giving us this respective fraction that we are looking for. So how do we construct these level 1 lists now? we could simply do a meet in the middle to generate them. So we split those lengths n, weight n over 4 vectors in lengths n over 2, weight n over 8 vectors. So if we concatenate them, we get what we need. But we already see that here the level 2 lists, they are larger than the level 1 lists, which is not optimal. So nothing prevents you from just repeatedly applying this, like adding another level of representations representing length n, weight n over 4 vectors as sum of length n, weight n over 8 vectors, introducing a respective constraint so that you only enumerate one of those representations, and from there you go in level 3 to a meet in the middle. So modulo some technicalities, further improvements, etc. This is how the Becker-Courant-Jou algorithm roughly works. And now we can talk about our new trade-offs. So here we have a similar illustration. We just removed these fixed constraints of n over 4 and n over 2. We exchanged by these variables L1 and L2. And we will indicate subtrees by these dashed boxes. So the main tree is T, and the tree T2 contains level 2 and subsequent lists, and so forth. So in the BCJ algorithm, we choose L2 such that there is one representation of the solution surviving these constraints. And if we choose it smaller, then there will be multiple of them surviving, which is what we do not want. And if we choose it bigger, then of course we are not guaranteed to generate a solution at all. But of course, if we choose it bigger, then we do also generate less other elements, not only less representation. So we have somehow a measure to control the size of those lists. And of course, this will propagate. So if we have smaller lists on level 2, we have smaller lists on level 1, and so forth. And of course, we are not guaranteed to generate a solution. So what we can do is we can iterate, like similar to the Schröppel-Shamir algorithm, we can iterate over this constraint. We can reconstruct this subtree T2 multiple times, an appropriate amount of times that we overstretched these representations that are at our disposal. And then we can apply this actually to any level of the tree. So we can, again, introduce a larger constraint on level 1 and repeat the subtree construction at level 1 multiple times, such that in expectation we generate one of those solutions. And yeah, so there are some technicalities that I'm leaving out here, so which actually enable us to somehow control the cost for each subtree generation, so that we can ensure that cheaper subtrees are generated more often, and therefore we decrease the time complexity further. Okay, this gives us control over all the sizes in the tree, but the level 3 lists here, they are, at some point they will dominate the memory consumption. So what we can do is we can exchange this meet in the middle by Schröppel-Shamir. As we've seen, this is a memory reduction technique, or more generally, you can use a framework called dissection. Okay, let us put this a bit into numbers. So here we have a plot of the time exponent over the memory exponent. So the time and memory are exponential. The time is 2 to the theta n. The memory is 2 to the lambda n. On the y-axis we see theta. On the x-axis we see lambda. We see that if the memory is not, so if we have unlimited memory, then the BCJ algorithm in the lower right is the best choice. And then we see as a dashed line a collection of more than 10 different trade-offs that were found optimal in different memory regimes. And as a dotted line, our improved trade-off. And actually, there is an improvement of the BCJ algorithm, which is a BBSS algorithm, which improves slightly, and we can also apply our technique to this algorithm to obtain an even better trade-off. Last but not least, let us have a look into the results for the information set decoding algorithms. So here we have a similar plot with the time and memory complexity of two modern ISD algorithms, the MMT and the BGMM algorithm. And you need to know that those algorithms, they can trivially be interpolated to a memoryless algorithm, which is this solid line we see. But if you, instead of trivially interpolating, use our improved trade-offs for the enumeration part of those algorithms, you get the dashed lines. And very interestingly, for the MMT algorithm, we get a result that is similar to the Schroeppel-Shamir result, that we decrease the memory consumption without any time penalty. Yes, as I said, we also implemented this, and we obtained new records on quasi-cyclic code decoding, and also better running times on McAleese. And in this table, we see basically the bit security reduction in comparison to previous works. So for example, for McAleese, if the memory is not limited, for the category 1's parameter set, which gives security equivalent to AES 128, we obtain 1 bit improved estimates. Sounds surprising that the time memory trade-offs gives an improvement if the memory is not limited. But you've seen that the MMT algorithm, the memory just got reduced, and memory is quite expensive in practice. So we obtain an improvement by this fewer memory access costs. Similar for bike and HQC. And but we see that for McAleese, for example, if we restrict the memory to 2 to the 60 bits, then that's where our trade-offs can shine, where we get 5 to 6 bits of reduced security estimates. So summarizing, we obtain significant speedups in the restricted memory regime, and we unify the subset sum landscape of different trade-offs to only 2 trade-offs, one our trade-off and one that is optimal in the very low memory regime. And yeah, we give the first non-trivial trade-offs for ISD with immediate practical impact. Thank you very much. The paper is online and the code is on Floyd's GitHub.
Is there any question?
Just a quick question. For the restricted memory, did you get those results for bike too, or?
For the restricted memory, so in the bike and HQC case, the algorithms don't use that much memory. So even for the optimal instantiations, they use 2 to the 50, 2 to the 40.
Okay.
This is why we don't have them here in the slide.
Thank you.
Okay, so on the GitHub, you have all the experiments? All the code is available?
Sorry, now I know what Deepanjan had for a problem because I couldn't understand it well.
Ah, sorry. On the GitHub page, you have all the experiments and the code?
Ah, yeah. On the GitHub page, the code is online. The experiments, so I think Floyd provided scripts to rerun the experiments. I don't know if all the experimental data that is basically used to generate things later is also in there in like raw format, but I can check.
Okay, thank you very much. So thanks, speaker, again. So the last talk of this session is a new algebraic approach to the regular syndrome decoding problem and implication for PCG construction by Pierre Briot and Morten Højgaard. And Pierre will give the talk.
Hi, so yes, this is a joint work with Morten, and we present an algebraic attack on the regular syndrome decoding problem. And with that, we want to attack parameters from pseudo-random correlation generators. So let's start with the decoding problem. So over FQ, so you're given this matrix G of size k times n, and this vector y, which has length n. And the goal is to distinguish whether this y is of the form mg plus e, where e is your error vector of Hamming weight t, or y is uniformly random. So also you have a raw formulation which is equivalent in theory, which uses a parity check matrix H and a syndrome S. And finally, maybe some of you are more familiar with the LPN assumption. So here you can view LPN where the number of samples is n and the secret size is k. But here, the number of samples, you must imagine it as always of the form k to the 1 plus alpha, where alpha will be constant between 0 and 1. So you don't have so many samples. And also, the noise, so the ratio t over n is extremely small. It's not constant. So in this talk, we are interested in the regular version of the problem, and it consists in choosing a very particular error distribution. So how do we do? You assume that small n is equal to capital N times t, where t is still the weight. And to generate your error, first you will pick t random blocks of length capital N, but of Hamming weight all 1. And the final error will be the concatenation of these blocks. So by construction, you see that your error has indeed weight t, but it's very particular. The non-zero coordinates will be at very specific positions. Okay. So why are we interested in this problem? In fact, already the decoding problem, or LPN, in this quite particular noise regime is already quite useful in secure computation. And on top of that, if you add the regular distribution, you can get even more efficient constructions. Okay. So here, I have taken the example of a pseudo-random correlation generator. So these are specific primitives in this area. And their goal is to generate what we call correlated randomness. So this is a very useful ingredient to build such primitives. So here I will briefly mention one example whose goal is to construct a vector OLE, so which was introduced by Boll et al. So I won't define a vector OLE, but just imagine that you want to produce some additive shares of a long vector U, which must look pseudo-random, so it will share between two different parties. So for that, they rely, for the first step, on function sequenceing. And what this primitive allows you to have is additive shares of a first vector, which is long, but which is sparse, which is this vector E. And actually, in our case, it will play the role of the error. Why? Because the second step, it's where LPN shows up. You will obtain this final vector U by applying the assumption on this error vector. And the important here is that you have two ways to do it. Either you are in the primal setting, and in this case, the vector U that you sent is your noisy code word Y, so mg plus E. Or instead, you can use the dual setting, and in this case, you send your syndrome, so E times the transpose of H. And why is it important in our case? Is that because it will lead to completely different parameters, especially the code rate K over N will be extremely low in the primal setting, but mostly constant in the dual setting, so think about 1/4 or 1/2. And finally, if you use a regular error, you can gain, in the first step, the cost of FSS will be smaller. Okay. So now, in terms of attacks on the regular syndrome decoding problem, or RSD, the thing is that they do not exploit the regular distribution. So you have this folklore attack, or which is called also Gaussian attack. So the goal is to guess k error-free positions in your vector, and then you just solve a linear system. You also have ISDs, which have been just mentioned by André, and you have statistical decoding. This is a similar technique, it's just the dual version. But the thing is that in this tiny noise regime, we don't really care because, in fact, the folklore attack will be the best one. Okay. And our contribution is to give a new type of attack on RSD, which is an algebraic attack. And this time, it will be really specific to the regular noise. It doesn't really apply to the plain version of the problem. Okay. And the nice thing is that we can beat some previous attacks, especially when the code rate is low. We will see why in a few slides. So these are typically the parameters which are used in the primal setting. Okay. So the first ingredient in an algebraic attack is an algebraic system, so how you model your problem into a set of equations. And here I will describe the case of a binary field, okay, because it's a bit more simple. Okay, so my unknowns in my system will be these error coordinates. I have n, and I also denote by ei one of the tip blocks in my error. So clearly, the first set of equations is this one. It's quite naive because you know that the error coordinates are in F2, so you have these equations for free. So the two other parts are a bit more interesting. They rely on the regular distribution because here in this vector ei, we know that there is only one non-zero coordinate. So this means that if you do the product between two distinct coordinates in this vector, you will get 0. So this gives you this second set of equations. And finally, over F2, you even know that this non-zero coordinate is equal to 1. So this means that if you sum all the elements in my vector, I get 1. And this gives me linear equation here. And the final system that I get, I just have to add this parity check equation, so which comes from your parity check matrix. Okay, so what are these equations? They are linear in our error coordinates. And how many do I have? Just as many as the number of rows is in H, so n minus k. And here you have to notice that n minus k is also equal to n times 1 minus the code rate. So you understand that when the code rate is lower, we can gain over these parts, and that explains also why our attack is more efficient here. Okay. So now I have my system. Let's talk about solving algorithms. So maybe you're familiar with Grosvenor basis or linearization, etc., but here it doesn't really matter so much. What matters is that you can express them in this kind of way. So the first step is to start with your system, and you multiply the equations by monomials. Okay. So once you have done that, typically you will fill a matrix which is called the Macaulay matrix, which is this thing. Here I describe the Macaulay matrix, the homogeneous version. This means that I start with polynomial fi's which are homogeneous. I multiply them in such a way that all the polynomials that I get, this polynomial mu fi's, are all of degree d. And then each row of my matrix will correspond to such a polynomial, and the column will be indexed by all the monomials of degree d. And actually, in the homogeneous case, there is a famous result which states that at some point, doing linear algebra on these matrices up to a degree which is called capital D here, I can solve the system. And clearly, in fact, this degree capital D, which is often called the solving degree, is the key parameter to estimate the complexity, because once this degree is known, the complexity is just the linear algebra in this matrix. So essentially, you just have to know the number of columns or rows, if you imagine that the matrix is square, and this number is exponential in capital D. Okay. So in the rest of the talk, I will try to explain how we derived the value of capital D for our system. Okay. So this is the key part in the paper, because you see that overall the system is quite naive. And we are going to do that with what we call the Hilbert series of an ideal. So I will consider this notion makes sense for homogeneous ideals. So here I pick an homogeneous ideal I. I also denote by RD the vector space which is spanned by all the polynomials of degree d. And finally, I to the d is just the intersection of I and this vector space. And in the case of an homogeneous ideal, I get a vector space of finite dimension. So the message about this object is that Hilbert series are really nice. It's a very great object, but sadly, they are not known in general for most of the polynomial systems that we have. So why is this object nice? So here you have the definition, but the important thing is that you see the rank of the Macaulay matrix appearing. So if we know this Hilbert series, we can recover the rank of the Macaulay matrices, and once we have the rank, we can predict the termination of the algorithm. Also, if you take a bit more time on this definition, you notice here that you have a dimension of quotient spaces, and this is typically the way that we are going to compute them, computing first this dimension, and then it will be trivial to get the final Hilbert series. Okay. So here, I don't have an homogeneous ideal, so I need to get one. And for that, I will take my polynomials and I will cut all the lower degree parts. So I get this system, AH. So this is a system which doesn't really make sense to be solved because we have lost the information on the lower degree part, but it will be important for the analysis. Another important property of this system is that it is zero-dimensional. So very quickly, this means that my Hilbert series will be a polynomial. And the crucial point here is the degree of this polynomial because it will be related in a very strong way to the degree capital D we are interested in. So essentially, in the remaining of the talk, I will just explain how we derive the polynomial, and once we have the polynomial, we can derive a cost for our solving process. Okay. And the important thing is that we are going to keep these two parts in our system one after the other, because one has a very strong structure. It is this part which just comes from the regular distribution. And it's structured, but hopefully we can manage to analyze it easily because you see that here my homogeneous parts of highest degree are really specific. They are just monomials. So in fact, we can get the dimension of the quotient spaces here in a very easy way just by doing simple combinatorics. We count the number of monomials which cannot be divisible by these two sets of monomials. And once I have my dimensions, I just can recover the first Hilbert series really easily. Okay. But now there is a remaining part which comes from the parity check equations, and here it's a bit trickier because I mean, we cannot really analyze them in the way that we have done for the structure part. And here we require an assumption. So what's the motivation here is that I said before that Hilbert series were not known in general, but it turns out that for random systems, these are one of the only classes of systems for which they are known. So essentially, we are going to treat these parity check equations as random equations. The only subtlety here is that we already have a quotient ring that we have analyzed. We need the randomness of these equations in this quotient ring. So this is our assumption here. So if you're familiar with it, it is really close to the notion of regularity, or more precisely here, semi-regularity, which was introduced by Bardet and Fogère. Okay. So from this assumption, we can obtain this relation for the Hilbert series. So here you have the previous Hilbert series that I have computed before, and here you must understand this factor as depending on the number of equations n minus k that we have added here, and the fact that z appears linearly just means that we have added linear equations. Okay. And finally, I said that we wanted a polynomial, so here we don't have a polynomial, so we just truncate after the first negative coefficient, because since my polynomial counts dimension of vector spaces, negative coefficients will not make sense. So finally, if I put all the results together, I obtain this Hilbert series. Okay. So I recall you this Hilbert series was a polynomial, and the degree of this polynomial was highly related to the solving degree of our system, because we had essentially d minus 1, which is equal to the degree of this polynomial. So how do we obtain it in practice? We conjecture a generating series with infinitely many terms, and we are interested only in the positive one. So we just pick the first non-positive coefficient. This gives us an index, and from this index we can recover the degree capital D. Okay. And finally, once we have the degree capital D, the rest is just trivial. We just have the cost of linear algebra. I assume that the matrix is square here, so I just have the number of columns, and the number of columns is just the number of monomials. Okay. And here you notice that the linear algebra exponent, I consider dense linear algebra. I do Gaussian elimination. I apply Strassenl algorithm. Okay. So actually, the best cost that we obtain is not really this plain technique. There are small improvements, but I will go very quickly because they are really standard. And if you want, you have the description in the paper. So the first one is what we call the hybrid approach. So it's finding a trade-off between system solving and fixing variables in the initial system. So here, I recall you that this error has a very small weight, a very small t. So the more clever way to fix variable in this case is just fixing variables to 0 in our vector, because with good probability, it will be the good guess. If you think about it, it's quite close to an algorithm, for instance, the folklore algorithm, also which is equivalent to Prange, but here we are going to fix much less variables. We don't need to fix k variables. We just need to fix the right amount so that the system that we obtain after fixing these variables is easier to solve. Okay. I have another trick which is called Excel with demand. So the idea is to use the fact that in our Macaulay matrix, all the rows are really, the Macaulay matrix is sparse because the row weight only depends on the weight of the parity check equations, even at higher degree. So at higher degree, we hope to gain on this part. So there is just a subtlety about the termination of this algorithm, but we analyze it in the paper also. Okay. And just to conclude, I will give some numbers. So maybe some of you just care about that. So here are the numbers. So here I just pick parameters which correspond to the primal setting. So here, if you compute the code rates k over n, you notice that it's very small. And in fact, the rows for which we gain the most correspond to even smaller code rates here. Okay. So essentially, it was what I wanted to say. So if you have any questions, I think we have time. So thank you.
Is there any question?
Yes.
Just maybe something stupid, but concerning the hybrid techniques, did you try the stuff we did with Vanessa, where you just do hybrid in a weird way that is slightly better for concrete dimensions?
Actually, for the hybrid case, we have not been very far because we were quite concerned in how fixing variables changes the analysis of the initial system we had. For instance, the only ways we considered hybrid approach was fixing error-free coordinates the same way in each block, almost, which gives us, we can keep the same analysis, essentially. We also tried fixing variables in some blocks, but not in others, but we have not, I think we could imagine any involved way in fixing variables, like any ISD algorithm, you can try to interpolate with this, and you could fix variable in this way.
So yeah, maybe we should discuss this offline, but it seems that what you really would like is to fix the variable in a way that would make big D decrease so that you get something better in the end.
Yeah, it's a good,
yeah,
yes.
Yeah. Okay, see you.
Thanks, very nice talk. Did you also run experiments to see if the systems coming from the parity matrices do indeed behave semi-regularly?
We tested for if you take a random parity check matrix, it works fine. The only thing we could try also, I think, is in this kind of primitive, sometimes they choose a parity check matrix which is d-local, so sometimes the weight in the parity check matrix is low. We have not tried, but I would say that if the system deviates from a random system, it doesn't really imply that, maybe if we do some further analysis, we can even obtain better results. If we, the structure can be like a difficulty to analyze, but it can be also benefit for the attack. So I don't know.
Thanks.
Hi, thanks for the great talk and the nice analysis. Can you clarify the novelty compared to the Aurora-Gay algorithm over structured LPN?
In terms of I'm not so aware of what they did. I'm more familiar with the Eurocrypt technique for LWE.
It's in the same paper.
It's the same? Okay, so I think
It's not the same, but it's in the same paper.
Okay, so I would say that the novelty in our work is not about the modeling because it's super naive.
Okay.
It's about the analysis because I think that Aurage was always analyzed assuming that the equations are regular, or I mean they didn't really do some theoretical analysis of the behavior of the system because they noticed that the system behaved as random one. In our case, we really try to analyze it. And I think the most interesting thing is that this kind of system where you have a random part and a part which is really structured, we can find it in other parts of cryptanalysis, and I think it can be applied to other kind of system like this.
So it's the analysis that is...
Yes, the Hilbert series, obtaining the Hilbert series.
Thank you, that's very nice, thank you.
Okay, so thank you, Pierre. And yes, we have to thank all the speakers of the session. So the next session is at 11:40.